Okay, so number 7, you can divide both sides by 2. Take the square root of both sides. Plus or minus will show up. Square root of 1/2 is the same thing as 1 over square root of 2. And what's another way of saying 1 over root 2? Yeah, root 2 over 2. It's the same thing, but it just feels more recognizable, maybe from a unit circle standpoint. We know sine is root 2 over 2 in within that pi over 4 family, but it's plus or minus root 2 over 2, so basically all 4 quadrants. Okay. We know all 4 quadrants will have 4 in the denominator. Second quadrant, you're going to have your numerator with the unit with the value 1 lower. Third quadrant, 1 higher than the denominator. And last quadrant is double the denominator, subtract 1. $32. Take the square root of both sides. Okay, think about your unit circle value. Tangent is y over x. So root 3 over 1, that's pi over 3. So basically everything in the pi over 3 family. Second quadrants will be 2 pi over 3. 1 less than the denominator, 1 more than the denominator, and then double the denominator minus 1. Okay. 33, what would your first step be? Yeah, factoring, right? GCF, take out or factor out or divide out a tangent theta. So when I take out a GCF, I'm really dividing by my my original expression by my GCF. So tangent squared divided by tangent theta. What's left over? Just tan theta. Tan theta divided by tan theta is 1. Yep, there's our factor form. Set both equal to 0, solve for theta. All right, where's tangent going to be 0? Tangent is y over x, so y over x, 0 over 1, that's 0. And also 0 over -1, that's also 0. So you got two places, 0 and pi. We would normally, maybe we could say 2 pi as well, but 2 pi is not part of our domain, so only 0 and pi is needed. Tangent theta minus 1 equals 0. Tangent theta equals 1. We know tangent is equal to 1 in the power over 4 family, but we're talking about positive 1. So tangent is positive in the first and third quadrant, right? Okay, 34. We can't do this. We can't factor a GCF out and set both equal to 1 and solve for theta. I know it feels like it could work, but if I want to set anything in factor form on both sides, I got to have 0 to show up. So it's not quite as easy as you would like. You got to bring that 1 over, and you got to do trinomial factoring. Maybe it feels more familiar to factor in terms of x. So if you want to factor in terms of x, star method would look like this: multiplies to be -2, adds it to be -1. Those two numbers will be -2 and 1. Divide out, and then we get x minus, well, 2 over 2, which is 1, x plus 1/2. I can bring that denominator up. Bring cosine back into your factored form. Right? Cosine theta equals to 1 at just 0 and 2 pi, but only 0 falls into our domain. Okay. Cosine theta equals -1/2. We know that's going to be in the pi over 3 family, but cosine is negative in the second and third quadrant. So 1 less the denominator, 1 more than the denominator. Want to make sure that we have some comfort level with not only unit circle values, but being able to solve these trig equations. We're going to need them down the road. Any questions so far? Okay, let's move on to talking about trig derivatives. You're going to find that these trig derivatives, I mean, we got to go through multiple rules here, but once you get past the rules, then everything should feel familiar, because we're going to go back and revisit product rule, chain rule, quotient rule, implicit, and those are all things you've seen every unit. So in a sense, you're just, you're learning your derivative rules, but then you're also strengthening your comfort level with all these other rules that we've been introduced ever since chapter 2. So go to page 9. Okay, so think of the top two, sine and cosine. These are kind of like your parent derivative graphs, or sorry, parent derivative trig derivatives, because all these other rules can be found using these two. Okay, so tangent can be found just by relying on sine and cosine, because all these trig functions can be written as sine and cosine. So if we just know these two rules, we can go through a series of product, quotient, and chain to arrive at these rules that we see here. Tangents derivative, cotangent derivative, secant's derivative, and cosecant's derivative. Well, we're just going to go through tangent's derivative just to see that that we can find all the derivatives relying on just sine and cosine, but I'm just going to move towards helping us create a way to, or begin working towards memorizing these 6 strict derivative rules, because we're going to have to need to access them fairly quickly. Okay, but the top two, sine's derivative is just cosine, and cosine's derivative function is negative sine. So if I want to find any slope on the sine graph, I can just insert the x value to the cosine. Whatever number I get back in return is going to be the exact slope of my original graph. Okay, but we're going to start off with tangent. We're going to work towards tangent's derivative, which we see here. So we're going to just rely on these two rules. Okay. I can rewrite tangent as what? Sine over cosine. Okay. We do have these rules individually, but because they're divided, we have to go through what rule to get to the derivative. Quotient rule, right? Quotient rule, we have everything that we need, but we're going to go through quotient rule. Okay. F prime g minus f g prime all over g squared. Okay, so f prime, what's sine's derivative? Sine, okay. Times the original g function, back to f. Okay, what's cosine's derivative? Yeah, right here, negative sine. All over denominator squared. All right, let's clean up our numerator here. Cosine times cosine is cosine squared. Negative sine times negative sine is positive sine squared. Okay, continue cleaning up. Does this numerator remind you of anything? Cosine squared plus sine squared equals 1, right? Remember the trig identity, Pythagorean identity, sine squared plus cosine squared equals 1. So we can make that replacement. And what do you think 1 over cosine squared can be? The secant squared, right? We know cosine and secants are reciprocal, so if I flip that cosine to the top, I get secant squared, and I've arrived at my derivative rule for tangent. Okay, we don't want to be going through this every time that we're trying to recall a derivative rule, but it's just nice to know that all these rules are just coming from these original two, sine and cosine. Okay, so we're not going to derive all these rules, but I want to move towards creating a way to eventually help us memorize these 6 rules that we need to know. Okay. So if you guys can put this at the bottom of your page, example 2 will not take up a lot of space. It'll be a quick problem, but I want us to practice writing these rules in what I think is a nice formats to help you remember these rules. Okay, so here let's write our trig derivatives. And I'll organize it in a way that hopefully will be helpful. Okay, so write it out this way. Start with sine. And we'll use u to indicate that a lot of times our trig function is not just x. And u kind of helps reminds us, oh, there's always going to be this chain rule involved, most likely like times u prime, just like how we've seen with a lot of our derivative rules. Okay, so if you organize it in this way, there's going to be some nice relationships here between tangent and secant. All these trig functions are on the second row, second column here, are all in alphabetical order. So you got COS, COT, CSC. Okay. And we're also going to see some nice relationships here between the ones that are across from each other. So sine and cosine have a certain visual relationship. Tangent and cotangent kind of resembles each other in terms of their format, and secant and cosecant have a nice relationship in terms of their format. So the more connections we make, I feel like the easier it is to memorize these rules. So the parent ones, let's go ahead and write those down. Cosine is just cosine of u times u prime, and cosine's derivative is just negative sine of u times u prime. So those are easy, right? They're just involving each other, just cosine has a negative sign. Okay, now tangent and secant, their derivatives just basically just involve each other. Okay. So tangent's derivative is secant squared u times u prime. And if you have this in front of you, then you can also get to cotangent because cotangent is also involving the ones below it and also a similar form. So cotangent is just negative secant squared u times u prime. Okay, secant's derivative also involves just the ones that's above it. So secant is secant tangent u times u prime. And cosecant's derivative is negative cosecant u cotangent u times u prime. There are some nice properties here with all these trig functions. All the C functions, okay, in alphabetical order. What else is common between all these trig functions that you see? They all produce what? Negative derivatives. So that's nice. That kind of helps you keep track of which derivatives are negative. All the C functions produce negative derivatives. If you can create this chart and put it at the top of your quiz, then you have all the trig rules in front of you. I'm hoping that every day we can, well, after tomorrow's test, that we can just recall, practice writing these rules. And so when we get to the quiz, it'll become much easier if we can practice building this table every day. Okay, so we're gonna practice use these rules for number 2 here. So if y is equal to sine of 5x, find y prime. This matches nicely with our sine u rule. So what do you think sine of 5x's derivative is going to be cosine 5x times 5, right? Yeah. Used to that u prime, right? We saw it with natural log. We see it with e to the u. Always look for that u's derivative. There's always that little bit of a chain rule going on whenever it's more than just an x. Okay, careful with the 5x and 5. These are not in the same places. We can't combine this and make the 25x. The 5x is inside the cosine function. This 5 is outside. So the most we can do is just separate them, put the 5 out in front. Typically like the coefficient out in front, so it doesn't get mixed up with that 5x inside the trig function. Okay, questions? Okay, page 10. One thing I want to point out to you is that the square root and the squared is not going to cancel each other out. The square root is outside the trig function. The x squared is inside the trig function. They're not in the same place, so we can't cancel those out. But maybe we can do something to rewrite this problem so we can see things a little bit more clearly. What can we do to rewrite this problem? Right? Everything raised to the what? 1/2. Yeah, let's get that radical to show us a different form. Okay, so guess what is involved with this process here? Chain rule, yeah, chain rule. Okay, your chain rule with trig functions is just going to feel a little bit longer because we got to go through a couple of different layers. But I think if we just still think of in terms of outside, inside, we should be able to get to everything that we need. The outside is that bracket to the 1/2, and that inside is the cosine of u, or that cosine of x squared, right? When we get to cosine of x squared, we'll do a little more chain rule. Cosine of u is negative sine u times u prime, so we can handle that derivative once we get to the inside. Okay. But let's do the main ones first. Okay, outside's derivative. What is that going to be? Power rule, right? 1/2. Bracket to the negative 1/2. What goes inside here? Yeah, don't do anything with that derivative just yet, right? Copy it down. And now that we're taking care of the outside, we can now move into the inside, but inside is going to be in a separate space. Okay, look back at your page here. Cosine's derivative is negative sine u times u prime. So let's do that here. Negative sine of x squared times what? 2x. So it does feel a little bit longer because we have to do an outside chain rule first and do an inside chain rule. Okay, any questions there? All right, so we'll do a little bit of cleanup. Just try to get it compressed into one clean fraction. Everything's being multiplied, so I can see the 2 and 2 can go away. I can cancel those out. 2 in the numerator, 2 in the denominator. And the rest I'm just going to place either in the numerator or denominator, depending on where they belong. So the x, the negative sine x squared, all this goes in the numerator. And the denominator, I can put this cosine in the denominator because I can force that negative exponent to come down. Okay, you can leave it in this form, or you can bring back the radical, doesn't matter. Okay, any questions? Okay, so a lot of this feels familiar, right? You know how to do this. It's just, okay, we just have to involve these new derivative rules. We'll come back and we'll do some of this after the test tomorrow. I want to go back to our test review and continuing highlighting some of the problems for us to go through.
When we have quizzes, will there ever be any questions that are like proof of rule?
No.
Wow.
Yeah. Want to show that connection, but it won't be on the quiz. There's homework for Trig, this Trig unit for Friday and Monday, this past Friday and Monday, but I won't check that until Thursday. But I'll send out a reminder on Wednesday. Once you have to focus on preparing for the test. Okay, so your test review packets. If you look at page 36, I want to keep coming back to this page here. You're going to be asked to find relative max, relative min for your curve sketching problem, but I'm not going to ask you to sketch your graph. There's curve sketching problem all over this packet. I really think page 5 or page 7. I think those are really good ones to go through. I just went through worksheet 3 this morning in my morning review. I will post that video on the website. So I also, those are also really good problems to go through if you have a chance to go through it. So I have the key on page 17, but page 15, I won't ask for domain and range, finding relative max, relative min, being able to find the equation of the tangent line, or slope at a point. Particle motion, we went through that problem this morning, and finding velocity, finding acceleration, evaluating velocity, acceleration at certain points, increasing, decreasing speed, increasing, decreasing velocity. This morning, we also went through a problem involving implicits, but anything with implicit with these problems, look for opportunities to expand using log properties, because then your derivative will be a lot easier to work with. I handed back your quizzes and, being able to expand logs, exponentials, involving product quotient rule, those all should be, hopefully you guys feel comfortable with those. Implicit differentiation, log differentiation, derivative inverse at a point. I want to make sure I kind of go through these again, make sure you guys are good with those. But yeah, just go through your packet. If you can do as much of those problems, if you feel comfortable with your packet, you should feel comfortable going into the test. And then tomorrow morning, I will go over worksheet 4. Yeah, page 29. So I'll go over page 29 and 30 tomorrow morning. Okay, so let's see. Let's try this here. On page 23, let's try this problem here. Find the derivative of y equals log base 5, 4 over x squared, square root of 1 minus x. how would you begin this problem? Right? Yeah, let's expand, right? We don't want to mess with that u value. It's just, it's not, it's just too much work, right? Why do a problem if you can split up into smaller problems? So keep this in mind. If I have log of a over bc, that's basically in that form, right? I got a numerator and two denominator terms. Your numerator is going to be part of a positive log expression, and your denominator will be part of a negative log expression. So if I have log of a over bc, the expansion will look like this: log of a minus log of b minus log of c. Let's do that. See if we can expand. And once everything is expanded and cleaned up, your derivative should feel like the easy part. Is there anything else we can do before we do our derivative stuff? Yeah, let's deal with the radical. We can also bring this exponent down here as well. I mean, it's not that big of a deal, but make it a little bit easier, but you'll be just fine if you left that x squared above and jump into derivative rule. It won't be difficult. We know that square root is really raised to the 1/2. Okay, so we have a derivative rule for log base a of u, right? A little bit of conversion has happened, and then u prime over u. Okay, what's going to happen with this first term if we were to find the derivative? Okay, and then what's u prime over u? All right, this is just a number, right? It's just a constant. So the constant will go to what? 0. Okay, so we don't necessarily have to find the derivative of that if we know this is going to go to 0. Okay, the 2 is going to stay. Log base 5 is going to go through a conversion, and then the rest is u prime over u. One half stays. U prime over u. Oh, sorry, 1 over natural log of a. U prime over u. Okay. Let's just do a little bit of cleanup here. I can get this down to 2 fractions. Let's call this one number 8 below. Okay, look at how number 8 is set up. Say it again? Yeah, this is a variable raised to a variable. We don't have a rule for this, meaning that we have to find a way to get it to look like a different form. So what category is this? This is log differentiation, right? So we gotta take the log of both sides because we don't really have a way of dealing with this exponent. But if I can get that exponent down to the base level, then I'll have some rules opening up for me to use. So we'll take the natural log of both sides. Because we don't have a rule for this, right? This is not power rule. This is not chain rule. This is not a to the u rule. I'm going to get my exponent set up and ready for my next step. Get that radical converted. Okay. All right, where can we put that exponent? Down in the front, right? We're not changing anything in terms of the overall value. There's no derivative here. It's just that this is part of a log property, right? Exponent can come down in front, which opens up our next step. Okay, we're ready for our derivative rule. What can we do on the left side? Chain, yeah, but a little bit of what? Implicit, right? We gotta track our dy dx's. Well, there's only one, but still have that going on. How about the left? How about the right side? Yeah, chain and product rule. So product is gonna be the first rule applied, and once we get product rule going, then there's a little bit of, yeah, we got a chain to worry about with this first portion. Okay, derivative 1 over y dy dx. Okay, f prime, this is where chain rule has to occur, right? Outside's derivative times inside's derivative. Okay, we'll do some cleanup on the right side, but there's not a whole lot we can do. At least we can get it down to 2 fractions, but I'm not going to ask you for a common denominator. But what can we do on the left side? Yeah, we want to get that dy dx by itself, right? That's our derivative variable. So when that y comes over, it's going to come over in the numerator. And I'll just try to push these into 2 fractions here. So -6 and 2 can reduce to be -3. X, natural log is in the numerator, and the square roots or this parentheses with -1/2 can be pushed down to the denominator. Okay, one final step. Something about that y there. Yeah, replace the y with the given function, right? Original. Let's see, one more suggestion I would like to make as you're studying for your test. Make sure you memorize how to sketch your natural log graph. Because if you have your natural log graph in front of you, then you can get so much information when you're doing your curve sketching problem. So your natural log graph is just an asymptote, order pair 1, 0 and order pair E1. Just from this graph alone, you can get so much information. You know where natural log of. Don't need to memorize any of these values because you can just read the graph, right? Natural log of -3, natural log of 0, natural log of 1, natural log of E. All this simply by graph alone can help you get so much information. So I really think it's really useful, right? With the no calculator tomorrow to be able to use this as your guide to help you ballpark a lot of these natural log values. I encourage you guys to study tonight, going through as much of the packet as you can. I'll do worksheet 4 with you tomorrow, morning review. But if you want to work through it tonight, that's great. I have the morning review video from last year. You can watch that as well. Okay, don't forget your phones.
Mr. Yang, if paper that came out of my packet, can you send a picture of page 36? Stuff that's gonna be on the test. The remind.
I give you another packet.
Okay, thank you. It was just so thick that it like, yeah, the last 2 pages. And then, I'll be able to take that quiz this week,
Sure.
since it's fairly short.
Yeah. Okay. sounds good. No, that's you're thinking log base 8, right? If I have log base 8 of 3 squared, then that's a number not log.
Yeah.
8 to the u, it's like 8 at 3x squared. Let's say you have the whole list. Natural log.
I thought.
It's slightly different. They both have natural log, but log has denominator, the exponential.
I felt like I did okay, but then I started